Welcome to Virtual Class, Organic Chemists. This video is going to be over notes numbers 10 through 14, which the material can be reviewed via Organic Reactions Worksheet 1 that I gave you. So please, after you fill in the notes, complete that worksheet. So, number 10. There are three main types of chemical reactions in organic chemistry. In inorganic chemistry, you had a bunch. In inorganic chemistry, you had combination reactions where you take two things and put them together. You have decomposition reactions where you break one thing apart and form two. You have single replacement where you have one thing replace another. You had double replacement. I don't have enough stuff to make that. Maybe it's like this. Double replacement would be two caps switching which marker they're on. And then you also had combustion reactions, which involved organic components, where you had something plus O2 yields CO2. But in organic chemistry, we essentially have just three types of reactions. They are substitution, addition, and elimination. So A, substitution reactions. A substitution reaction would be like this. So let's say I've got bromoethane. And with that bromoethane, I'm going to react it with a more electronegative chlorine. Well, chlorine is more electronegative, therefore chlorine is going to be able to kick out and replace bromine. And then I'm going to have my bromine kicked out. So that would be a single replacement. I have one thing combining and joining the chain. Elimination reactions. Elimination reactions are going to be along this line. So let's say I've got chlorine here and I've got chlorine there, and I'm going to have it react with something that will pull the chlorine off, and then I get a pi bond to replace it. So this chlorine gets pulled off, that chlorine gets pulled off, and then in between I form a double bond. So a substitution reaction involves sigma bonds or pi bonds, no change. Whatever I start with, I end with. Elimination reactions have, I will always increase the original number of pi bonds by 1. And then the last type is the opposite of elimination, addition. Addition reactions would be starting with some pi bonds and reacting it with, I could say, chlorine, and breaking that pi bond and replacing it with two sigma bonds. So those are the three main types of reactions. Number 10, A, substitution, B, elimination, and C, addition. Number 11, substitution is a reaction in which an atom or group of atoms is replaced by another more electronegative atom or group of atoms. Substitution reactions involve sigma bonds. One sigma bond breaks, another sigma bond forms. B, substitution reactions often involve a halogen. Why would they involve a halogen? Well, if we have substitution reactions, remember we're kicking something out of the original molecule. And if I'm kicking something out, I would need something that could kick it out, something that would replace it. And so the electronegativity of a halogen is a great place to start. Another great component, a great organic substance to replace or cause substitution to occur would be oxygen. So if I started with chloroethane, and I reacted it with sodium hydroxide. There's my oxygen, my high electronegative element. Let's say it's dissolved in water, HOH. What's going to happen is this hydroxide is going to kick out the chlorine. Why? Because oxygen, after it dissociates from sodium hydroxide, or after it dissociates from water, is going to produce a very negative, very electronegative oxygen atom that can then kick it out, and then I would make ethanol. A, or 11BI. A halogen replaces a hydrogen atom, and an alkane produces an alkyl halide and a hydrogen halide. This is known as halogenation. Genation, the creation of. Halogen. So halogenation, the creation of an alkyl halide. So, if I were to read the following, methane plus chlorine yields chloromethane plus hydrochloric acid, would you be able to write it? So pause the video and give it a try. All right, so I've got methane reacting with chlorine, producing chloromethane, and hydrochloric acid. Well, methane, I kind of have to draw it this way. So there's methane. I'm reacting it with chlorine. Chlorine's diatomic, Cl2. And I said I produce chloromethane. In other words, a hydrogen is removed. A hydrogen is kicked out. Why? Because chlorine is more electronegative. And then I produce chloroethane, or that would be the skeletal structure right there, and hydrochloric acid. So this would be one where I'm illustrating all the components that are involved. The hydrogen that was pulled off is going to bond with the other chlorine that was here in this diatomic chlorine. The other chlorine that was a component of this diatomic chlorine. If I draw the Lewis structure, we'll see both. So one of these combines with the hydrogen, the other replaces it, or substitutes it out. II, so 11BII, a base with an abundance of hydroxide ions. Remember, hydroxide contains oxygen. Oxygen, highly electronegative atom. Reacts with an alkyl halide, producing a salt and an alcohol. Since fluorine is extremely electronegative, and I wrote fluorine as though it's like a floor or something. It's Fluorine, not fluorine, but fluorine. It's so electronegative. It is not often used to make alcohols because it's a terrible leaving group. Because it's so electronegative, it's hard to make it move, make it go on. So, I'm going to read a statement, see if you can write it. Remember to pause the video after I read it to see if you actually got it right versus just copying my work. And so, this time let's react iodoethane with potassium hydroxide. And we will produce ethanol and potassium iodide. So again, iodoethane reacts with potassium hydroxide, yields ethanol and potassium iodide. Pause the video, see if you can write that. So, we've got iodoethane, Eth2, iodoiodine, iodoethane. We're reacting it with a non-organic potassium, K, hydroxide, OH, so a salt. This potassium hydroxide will dissociate in solution into potassium ions, which I don't care about because it's a metal, and hydroxide ions, which I definitely care about. Hydroxide, remember, is highly electronegative. Because it's so electronegative, it can push iodine out. We'll spend more time next chapter talking about that. But right now, we should be able to write that. So there's ethanol. Here's my hydroxide ion that kicked out the iodine. And then my inorganic byproduct, potassium iodide. 12. Elimination. Elimination is a reaction in which elements of the starting material are lost, in quotes, and a pi bond forms. So I'm going to eliminate two sigma bonds, and to stabilize, those two carbons are going to retain an electron that's zipping around in an unhybridized orbital, and those electrons will then influence each other to stabilize through the formation of a pi bond. Elimination reactions involve two sigma bonds that are broken, results in the formation of a pi bond. 12b, the most common elimination reaction occurs when one atom is eliminated, and that atom is hydrogen. And the other atom that is eliminated is a more electronegative atom than carbon, like chlorine, fluorine, bromine, iodine, etc. C. Elimination reactions can be used to form alkenes and alkynes. Organic chemists get excited when they have alkenes and alkynes. And the reason for that is because now it's kind of a universal, what do you want to add to a tool? So I'm going to read another statement here, see if you can write it out. Pause the video, don't just copy down what I'm writing on the board. So, we've got bromoethane, and we're reacting it with hydroxide ions. So those hydroxide ions could be in lithium hydroxide, potassium hydroxide, sodium hydroxide, calcium hydroxide, whatever. I've just got a bunch of hydroxide floating around. I'm going to make ethene and water, and bromine will be eliminated. See if you can draw that out. Thank you. All right, so we started with bromoethane. Bromoethane, two carbons, F. Remember I said there are two things eliminated. I said one of those things is a hydrogen, and the other is the more electronegative atom like bromine. I said I'm reacting this with some form of hydroxide containing ions. So what is going to happen is the hydroxide is going to pull off a proton. Why? Well, what's around the bromine is a bunch of electrons. All those electrons are not going to like hydroxide, but this proton will. And so I'm going to make that HOH. Well, as this hydrogen is pulled off, this carbon right here, could call it an alpha carbon, even though that's the alpha carbon right now, but based on what I'm talking about, this is where the action is happening. As that proton is being removed, this is becoming increasingly negative. As this becomes increasingly negative, this bromine with its big fluffy electron cloud is going to become uncomfortable and it is going to want to leave. And as a result, I'm going to make ethene, and my bromine got kicked out. And if I have more than one atom, which I definitely would if it's in solution, I would have some bromine in the solution. Another one for you. Hydroxyl cyclohexane being combined with sulfuric acid. This time I'm going to yield cyclohexene. I could say one cyclohexene, but cyclohexene and water. See if you can illustrate that. Again, it's hydroxyl cyclohexane and sulfuric acid is going to yield one cyclohexene and water. Pause the video, see if you can write that out. All right. So, hydroxyl cyclohexane. There's my cyclohexane. Hydroxyl means on it I've got an OH group somewhere. So I could also call this cyclohexanol. Cyclohexanol. And I said I was reacting it with sulfuric acid. Sulfuric acid is different than hydroxide, so this process will be different. But sulfuric acid, remember, loves to release protons. Well, if we think back to what previously happened, what does hydroxide love? Hydroxide loves protons, and so it would pull it off. And when this gets pulled off as that proton floats by and they're attracted, we're going to make some HOH. And as that happens, this is going to become increasingly positive because the highly electronegative oxygen will pull with it the electron. And as this becomes more positive, an adjacent proton, like charges repel, will be pushed off. And what would I result in making? I would result in making one cyclohexene and my water right there. 13, addition reactions. Addition reactions are interesting. So an addition reaction is one where elements are added to the starting material. Addition reactions are going to involve a pi bond, the weaker, unhybridized electron from each of these carbons, a pi bond being broken, and two new sigma bonds being formed. In other words, I'm doing the opposite of elimination. Addition and elimination are opposites, so that makes sense. B, addition reactions are an important method for introducing new functional groups to organic molecules. C, when the reagent is water. An alkene is said to undergo while I'm adding water. If you're adding water to yourself, aren't you hydrating? Therefore, let's literally call it what's happening. We're adding water to a molecule. It's said that that molecule undergoes hydration, a hydration reaction. Hydration reactions usually occur when an alkene and water are heated to about 100 degrees Celsius, increase the interactions, in the presence of a strong acid, like hydrochloric acid, HCl, or sulfuric acid, H2SO4. Notice HCl is simple, low steric hindrance, often going to cause that HCl to be involved in this interaction. H2SO4, bigger, clunkier, more steric hindrance, cause it to be acidic and introduce protons, but that HSO4 byproduct is big and clunky. We'll learn more about that next chapter as well. So, hydration reactions, CI. Hydration reactions produce alcohols. Well, how does that work? Well, let's think this through. Let's start with ethene. And ethene, I'm going to add to it water. I'm going to hydrate it. Well, if I start with ethene and I react it with HOH, why does this make an alcohol? Well, look at it. Remember, HOH has two parts. It's got this acidic part, which is a proton, and it's got this basic part, which is a hydroxide. So I've got a positive component when this bond breaks, right, that electron will stay with hydroxide. Oxygen is more electronegative. When that bond breaks, this proton becomes more positive. Well, what do I have a bunch of here? In this pi bond, I have weakly held electrons. That's going to be a negative region. This proton would love that negative region. And so what's going to happen is this pi bond is going to swing over and bond with that proton. Well, as that pi bond is split and no longer shared between these two carbons, but rather it's now a sigma bond shared between a carbon and a proton, this is going to become increasingly positive. Well, who's going to love that carbon that just lost an electron to this proton? My hydroxide. And so I make ethanol. So that's how that addition reaction takes place. D, when the reagent is a halogen. Halogens, remember, are Br2, Cl2, F2, I2. A di-substituted, two substituted, two substituents. A di-substituted alkyl halide. See, if I add Br2 to this molecule, I would get a bromine here and a bromine there. These usually do not require catalyst because bromine, chlorine, fluorine, iodine are highly electronegative. They don't necessarily need any additional energy to cause this to maybe split up, to cause this increase in interaction. Chlorine, fluorine, and bromine will find it all on their own. So, ethene plus bromine. Ethene plus bromine. So let's start with our eth again. Ene double bond. So ethene reacted with bromine. Something that's important about this, ethene is clear, colorless. Bromine is red. So this is a good way to test, have you broken all of your pi bonds? Because when bromine interacts with ethene and I produce 1,2-dibromoethane, when I produce this, this is also clear. So if I add a drop of bromine and it disappears, clearly I had more pi bonds. Because red, bromine, plus a pi bond yields a clear solution. But if I add another drop and it disappears, and another drop, it disappears. Every time I'm adding a drop, I'm adding a bunch of bromines that are breaking a bunch of pi bonds. But as soon as I get to the point where I add a drop and it doesn't disappear, what does that tell me? That tells me I have no more pi bonds left. So bromine is a great tool for organic chemists to test, are my molecules saturated? In other words, am I out of pi bonds? Number 13E. Because of this bromine, which is red, it can be used to test to see if a solution is saturated, based on what I just talked about. Because it's red, clear, clear. If I keep adding red and it keeps disappearing, I have no pi bonds left. If I keep adding red bromine to my vat of ethene, and all of a sudden a little bit of red sticks around, that means I'm out of my original starting material. 13F. When the reagent is a strong acid, like HCl, HBr, etc., aka, maybe strong isn't the best word here, but a simple acid, like HCl, HBr, or HF, a monosubstituted alkyl halide is produced. Mono, one. Substituted substituent. Alkyl halide, it tells me what my substituent is. Because halogens are involved, catalysts again are not generally required. So this time let's do ethene plus hydrochloric acid. Ethene plus hydrochloric acid. I'm going to start with my ethene again, but now instead of having that di-substituted alkyl halide as a product, I'm going to just start with HCl, hydrochloric acid. Remember, this will dissociate into two components, a positive proton and a negative chlorine. The positive proton would seek out that pi bond, that rich area of negativity, and it would bond. And then that would leave behind a positive carbon on the other side, where that chlorine would then bond. So I have a monosubstitute alkyl halide. So what is a benefit to a monosubstitute alkyl halide or an acid as composed to a disubstitute alkyl halide? Well, a monosubstitute alkyl halide will only allow one path for growth, one path of a high electronegative functional group, which is easily manipulated. If I have a disubstitute alkyl halide, like I did when I combined my ethene with, let's say, chlorine, Cl2, now I get two chlorines, so now I could have substitution reactions where I'm manipulating off both ends of that pi bond. Now, why did I draw this with a chlorine up and a chlorine down? Well, remember, chlorine has around it electrons. And so by drawing this, I'm also indicating that I understand the foundational rule that like charges repel. But because there's not a double bond, it really doesn't matter where I draw them, because remember, both ends of this molecule will be able to spin. So if I were to read this top equation, I would say ethene reacted with hydrochloric acid produced chloroethane. G, the addition of hydrogen to an alkene to produce an alkane is referred to as hydrogenation. So we've got hydration where we add water, HOH, to a molecule that has a pi bond. Hydrogenation, or hydrogenated oils, perhaps we've heard of this phrase before. Hydrogenation is when I add hydrogen. Now a big change between my hydration and my hydrogenation, between my halogenation and between my acidification, or that's not really the word. When I combine an acid with my alkenes. When I'm using hydrogen, hydrogen is not as electronegative as my chlorine, my halogens, or my chlorine here. And so, because I don't have that high electronegative atom, I'm going to need for hydrogenation to occur, I'm going to need a catalyst. Hydrogenation does require a catalyst because this is a reduction reaction. Metals, remember metals are kind of like a cell phone, something that allows for a quick communication, a quick transfer of electrons, but they're not used. Good metals are platinum, palladium, and nickel. So now I'm going to read, see if you can draw this out. So I've got ethene, I want to hydrogenate it. So I have ethene being hydrogenated with hydrogen gas. Platinum is used as my catalyst, and I will produce ethane. So pause the video and see if you can correctly illustrate ethene being hydrogenated with hydrogen gas using platinum as a catalyst producing ethane. Go. All right, so I've got ethene, boom. Being hydrogenated with hydrogen gas, redundant. Hydrogen gas will hydrogenate. H2 is how we write hydrogen. It is diatomic, and because it's a gas, let's do a lowercase g. And I said platinum was a catalyst. It's a condition, so I put it below. And what's going to happen is I'm going to hydrogenate it. I'm going to reduce it. 14. Addition and elimination reactions are complete opposites in terms of bonds. Addition make 2 sigmas and break 1 pi. Elimination does the opposite. Elimination makes 1 pi by breaking 2 sigmas. So let's go through one quick example here of that. So if I want to have, let's say I start with ethane, and I want to turn it into ethene. I want to get to ethene. Well, right now I just have hydrogens on it, and hydrogens are not the easiest to manipulate. But if I react it with something like HCl first, chlorine might seek out and replace a hydrogen. And now what have I done? I've done a substitution reaction. I broke this sigma bond between the carbon and the hydrogen, and I replaced it with this sigma bond between the carbon and the chlorine. Now I have something that can be eliminated. I can get that chlorine to skedaddle, and I can get a proton to skedaddle. So how do I get that to occur? Well, to get it to occur, let's react it with sulfuric acid. So if I react it with sulfuric acid, that acid, remember, releases protons. Well, that proton could cause this chlorine to leave. And when that chlorine leaves, this proton could then leave, and then I would produce ethene. If I were to react it with a base, like sodium hydroxide, so if I were to do the top scenario, this would get pulled off first, and then the hydrogen would get pulled off second. If I were to react it with sodium hydroxide now, this would be pulled off first, and then this would leave second. But both would result in the production of an alkene. Now when I have that alkene, this reaction was, I broke 2 sigma bonds. Notice this sigma bond is gone, that sigma bond is gone. They aren't illustrated here. And in their presence is a single pi bond. So this is an example of an elimination reaction. And when I have an elimination reaction, I can undo that elimination by reacting it with, let's hydrate it. Let's hydrate it. And if I hydrate it, I'm reacting it with HOH. I'm adding hydrogen and hydroxide to this, and I'm going to make ethanol. And so I've got my substitution reaction where I place hydrogen with a more electronegative chlorine. Then I've got 2 scenarios for elimination to occur where I get my leaving group, my chlorine, to go. And I remove 2 sigmas and replace with a pi. And then I go from 1 pi to 2 new sigmas. And this last one would be an addition reaction. So hopefully that clears up the 3 main types of reactions to some degree. The chemistry behind it is something we'll be spending a lot of time with next chapter, not so much right now, but understanding that elimination is the removal of 2 sigmas and the replacement with a single pi. Understanding that addition is the breaking of a single pi bond and replacing it with 2 sigmas, and substitution is no change in sigmas or pi's from start to finish. Thank you.